So it's making sense or making it up in the sense that some of you might be like me, physicists or mathematicians. We like to understand, a process from A to B and all the steps in between. And often when you're like me, not an AI expert, you use the tools that you are given that are amazing, but you don't really understand what's happening. So in that sense, it's possible that you're making up some information, some results, some maps, and that they are partially wrong. This can happen also when you do physics, by the way, but your mistakes are different. They're made from perhaps a wrong understanding of the physics or a wrong description. So I will start in my first part. I will still show examples of nice things we've done with physical approaches, where we have a forward model, and then we try to invert and understand parameters of sea ice in particular from space, but with a physical understanding. Then I will talk more about classifications and regressions from an AI perspective. And at the end, I will show also some other techniques, maybe a bit more modern, deep learning, different forecasting approaches we've tried and so on. So the funding is from SIOS, so thanks so much. Shall I say, how do you pronounce it? SIOS? SIOS. So thanks so much for having me. It's a great opportunity. It's my first visit in Svalbard as well, so I'm very, very excited to be here and very impressed by the place and the people and so on. So thanks so much. The other funders are general my funders, so the Center for Polar Observation and Modeling and Earth Sciences, the Department of Earth Sciences at UCL. So as I said, when you're from the 80s, like me, you used to do physics. You didn't have a computer, you didn't have internet, so you were doing problems with textbooks. You were learning equations. You were trying to understand nature or physi in Greek with an old school understanding, which is mathematical or physics. So I'm asking a bit provocatively: would AI have discovered gravity, quantum mechanics, etc.? I just want you to remember that some of you are younger, most of you. If you just use AI, you're missing out on a lot of understanding potential. So, and you might be doing things a bit in a black box way that it's not ideal. Of course, I would say that because I'm biased. I'm a physicist, so that's fine. I just put as a bit of a joke because I have a little interest in drawing, and it will come back in the later this afternoon when we do a 100 exercise. I would like to combine a bit drawing. Two of my recent interests, which are AI and drawing. So we'll do that a bit later in the practical. But there is a lot of AI that's been used and discussed in art. So there's DAL-E program you might have seen. You tell to the program, draw me we saw that yesterday in the presentation, draw me a polar bear with plays with kids, and then you have a work of art. So this is a philosophical question. Is it really art? I don't think so, because art is something that expresses our own kind of interaction with the world, but perhaps it happens via AI. The reason I'm showing that is because also some of the high resolution imagery or not high resolution satellite imagery from the polar regions and other regions of the planet are really beautiful. I could very easily, unfortunately, the contrast is not perfect, but this high resolution imagery of Sentinel-2 of Canada, I should have picked Svalbard, but Svalbard would be as beautiful. You could print that and put it in your room in a nice frame. You would be probably not looking too bad in an art gallery. But is that art? Probably not either. This is the dot, Malevich, right? The white square of Malevich. So this is white on white, just to highlight that snow and sea ice and the polar regions have this extra challenge for remote sensing, which is that we need to see a white thing, a cloud, on top of another white thing, a snow, on top of another white thing, sea ice. So this can be tricky even for the best AI algorithm. So yeah, it is Malevich, 1918, the white square of Malevich, white on white. And so I have a little bias again. I'm a little amateur sketcher. So these lines that you see here and the lines that you see here, hopefully in the practical, you will see them together. And we will try use a software called Iris, where you can draw on a high resolution imagery and kind of get the best of sketching and AI together. Of course, mathematicians and statisticians will tell you even more than physicists that AI is nothing new. They've been doing that forever. They understand everything. They developed statistics and mathematical tools. It's nothing new. It's just rebranded by maybe funders, Google and politicians to get grants. And it's an old idea. Some of that is probably true. I also think AI has a lot of potential that is perhaps beyond even some mathematicians that are very smart. But I should also say, maybe too many of us use AI and too few understand it. So I'm one of them, I'm afraid. So, but just be aware that when you do that, you perhaps don't make deep discoveries as much as if you are an AI expert. So I would recommend you to work with AI experts if you can, like we've had here all week, and not just apply it blindly. But anyway, I'm not an AI expert. Nevertheless, it's going to be fun to look at some of the results. We got some of them with AI experts. So let's do it. But let's do it after the first part. The first part, I'm going to talk to you a little bit about inverse modeling, which is the old school way maybe of doing stuff, but it has overlaps with AI. So you have a forward model. In this case, it's called theta of D and M. D are observations and M are your model parameters you're trying to invert to retrieve from, I don't know, it could be sea ice thickness, for example, or snow thickness from space. D could be the observations of the satellite radar altimeter. And then you have a prior understanding, rho of D of M, of both the observations and the model parameters. And mixing the observations with the model and the prior understanding of your model parameters can allow you to constrain the posterior distribution in this kind of Bayesian statistical way of understanding this kind of methodology. And so inverse modeling is this line of inquiry. Probably the guru of inverse modeling is this guy called Tarantola. He was teaching in France in the 90s, and he has inspired a lot of people to do inverse modeling. So I encourage you to look at his book. So one of the applications we did with inverse modeling was, the first one was with my postdoc Harry Houghton at UCL. We tried to look at 3 data sets from space. So that gave us the wind, the ocean currents, and the ice drift. All of this can be derived from space. Actually, the wind we took from reanalysis. And if you remember the work from Nansen from more than 100 years ago, he discovered that the drift is at an angle from the wind to the right, typically in the northern hemisphere. And so you have a forward model. You have an equation to characterize how the ice responds to the winds and the currents. And this ice is moving. You can see it from space. It's this term called U. And it's responding to currents and wind. And the parameters you're trying to retrieve are drag coefficient in our case. We want to understand how rough and rugged the surface of the ice is. So this is what controls how much of the wind will push the ice around. So having obtained ice drift, wind speed, and geostrophic current over a large part of the Arctic with satellite measurements, we were able to invert this equation to retrieve these parameters. Again, if you have observations of this, and where is the last one? I guess it's part of that. You can invert for other parameters, turning angles, drag coefficient, and so on. The tool we did to sample these parameters in an effective way came from seismology, and it's called a neighboring algorithm. If you're sampling the parameter space M, there's a very effective way to go finer and finer in places where that are meaningful to retrieve the parameters you're interested in. So we retrieved drag coefficient, as is shown in this last map, for the Arctic in different places, and we were happy about that. But there was no AI as such. This is forward model, understanding of the physics, and deducing parameters. So I'm giving you another example of that, perhaps a bit more simple. You have CRISA-2. This is the satellite we're very proud of at UCL because we developed it and proposed it more than 20 years ago, and it's been flying for 12 years now. And it's been a breakthrough for our understanding of the polar regions. So CRISA is this big orange flying object that's 700 kilometers high. It sends pulses on the surface that bounce back. And so you're trying to measure the distance from the satellite to the sea ice, to the ice, or to these regions that are leads, broken up ice. And you measure the difference between here and here to deduce the freeboard. And from hydrostatic equilibrium, deduce the total ice thickness. So CRISA-2 is a method an altimeter that allows you to measure ice thickness. In practice, you can also use it over open ocean, and this is what is shown here, where you do the same thing. You send your echo, it bounces back, And what you collect are these echoes in different modes of operation, SAR or low resolution mode. And the echo shape will be very dependent on the surface you interact with the pulse. That's a kind of rectangular pulse. So the footprint will collect lots of information, send it back. What we did here is to fit an analytical model of the full description of the echo plus interaction with the ice plus bouncing back, where you have some parameters you're trying to invert: the distance from the satellite, the roughness of the ice or snow, depending on your understanding, and other parameters. And so you see you have a very good fit of this analytical, semi-analytical model. And that's another example. When you have a good understanding of your physics, of the electromagnetic wave, ice interaction back, then you're able to understand and probe really the system very finely and really understand what's going on. So from this, we were able to retrieve significant wave height over the entire polar oceans, Arctic and Antarctic, again with Harry Houghton, who has been a postdoc with me for a few years. So that's published in last year. So we can do the same. This is some work we're doing now with actually Carmen, who's in the room. So we're trying to do the same ideas, but to retrieve snow thickness. So you have different frequencies of operation of altimeters. Laser, you have ISAT2, I think is, no, there is no laser. Which one is the laser? Okay, one of them is the laser, probably the red one. The red one should say ISAT2, it's not Altica. In green, it's Altica, operating in Ka band frequencies, and in yellow, it's CRISAT2, operating in Ku band frequencies. The basic understanding is that Ku goes through the snow, Ka doesn't, and ISAT2 doesn't either, it's a laser. In reality, it's more complex than that. Both Ka and Ku can and cannot penetrate the snow, so we're working on that. But with this and the penetration factor of main scattering depth, alpha, tells you how deep the radar goes. If you do that, you have several equations, and you're trying to invert HS, snow thickness, and HI that is hidden in here. The ice free body contains the ice thickness. You can just invert that ice thickness and snow thickness from space, from your observation. Again, you have formulated a problem like a problem times your parameters equal observation plus noise. You can invert that. There is no AI needed here. So lastly, for this physically based methods, we did some exciting work with Jack Landy from Norway, from Tromsø. He's based in Tromsø at the moment. So instead of doing a simple analytical description of the surface as a rough Gaussian distributed elevation, we simulated exactly the topography of the footprint of the radar. So this is a 8 kilometer by 300 meter region of the Arctic sea ice, just under collocated with an actual footprint of CRISAT2, but also taken from airborne data. So there was a collocation of airborne measurements, satellite, and so we were able to exactly take the information of the real topography, simulate all the interaction between radar, topograph, all the facets of the topography back to space, to the satellite, and we were able to simulate an echo in blue here that looks very much like the exact coincident echo from CRISAT2. So we're satisfied that we are able to do direct numerical simulations of the radar ice snow interface interaction. So with that in mind, we then have the possibility to generate millions or thousands of synthetic topographies with different roughness, different properties, in order to create a database of echoes that can then be used for fitting real echoes and inferring properties of the surface. So this is a kind of another brute force way to create a database of surfaces that can then be used into AI frameworks. But here we just use it in this kind of direct physical way. All right, so that was a few examples of how physics can still be useful. You don't always need AI. Now let's stick to the topic of this class. Let's talk more about classifications, regressions, and I will give you a list of examples that we worked on. The difference, I guess we had it in the several talks already this week. Classification deal with discrete categories, while regressions usually deal with a continuum set of values. So I'll give an example of both. I'll talk about some of these examples here, random forest and so on. And we'll do some of these examples in the hands-on class later on this afternoon. So a first example of a review paper and a paper by Müller in 2017 is this unsupervised classification of echoes. So the echoes I just showed you earlier, they have different shapes. Some are very picky, some are very broad, some are intermediate. So there is a way, in this case, using K-Medoid's clustering technique, to come up with 30 categories. In that case, the number is fixed, but you can classify 300,000 echoes into categories, but in an unsupervised way. So the system, the AI is doing categories itself that are organized in similarity levels in kind of some kind of metric and technical K-Medoids. And so you can then visually allocate this. You can take the average of all this, each category, and compare with some ground truth from an independent data set. And you can see that some of them are associated to oceans, those that have a large trailing edge. Some very picky are a lead, an open ocean in the middle of ice. Some are unclassified, they're too messy. And all the rest are sea ice. So this is a nice system to let the system show you what are the patterns. You don't always need to train. You can also let the AI find patterns without you training. And then you can try and understand what these patterns are. But of course, you have supervised classification as well. So this is another approach where you have a training data set. And then you do similar things with the echoes. You classify them into categories. In this case, it's using a neural network method described in a paper by Poisson. I think it should be here, but a colleague from TLS. And you can see that you have leads, ocean, and sea ice categories that are very clearly present, and others are too messy, and you don't want to use them in this method. So here we talk about neural networks in this example. Sorry, the review paper by Quartley we wrote 3 years ago is describing that. So this is, for me, quite beautiful as well. It's also very visual, right? So you have sea ice and leads. And the challenge in the community is to identify the leads. The leads are very important in many ways. First, for altimetry, we need to know where is the lead, where is ice. But of course, the lead is also an intense source of heat exchange and gas exchange in the winter in particular. You can have thousands of watts per meter square fluxes in this latent heat flux and sensible heat flux lost to the air from the ocean. So I think it's something like 50% of the heat exchange in the winter occur in these tiny regions, which are only 1 to 5% of the Arctic. So they're very important kind of breathing systems for the Arctic, for the ocean. So you need to know the location, the size, and so on. So detecting them is very important. It's also important for shipping. If anyone of you has been on an icebreaker, the captain is seeking those leads, right? So detecting those is very also operationally important. So this is 4 examples here of how to use the radar altimeter shape, the echo shape that I showed you earlier to detect these leads. On the left, there are 2 traditional methods that look at how picky an echo is and says those are very picky, in a nutshell, are leads. Those are broader, are sea ice. So this is working quite well. In red, you have things that are classified as leads, but it has a lot of errors. Sometimes the ice is also quite flat, and perhaps it appears as picky, while it shouldn't. So a colleague of mine who was at UCL a few years ago called Sang-Yoon Lee, I thought I had his name, but no. Sang-Yoon Lee tested a decision tree and a random forest approach, where he had the manual classification of leads and ice and applied these AI tools and got a much better agreement between leads classified from radars and the underlying observation. In this case, I believe it's MODIS. So it's just an example when AI can be performing better than a simple empirical methodology. We will do something similar in the hands-on practical that I've devised with an intern that worked with me this summer called Weibin Chen. So what we will do this afternoon is do the same work, but instead of what Sang-Yoon Lee did 3 years ago, we now have Sentinel-3. So Sentinel-3 is this image here, but Sentinel-3 has this amazing property that it has optical with an instrument called OLCI, very much like MODIS, and altimeter on the same place at the same time. So this is like the holy grail for AI people, because you have millions of training data sets. that I'm going to start playing with you this afternoon. So this track that you see, the red line on top of the image that's underlined, it's consistently like that. So you have the Sentinel-3, the Sentinel-3A and B, they're both in orbit for 5 and 3 years, 6 and 4 years. And so you have millions of data sets. Every red point here or blue point is a footprint of the altimeter. And you have a collocated image pixel of 250 meters wide. So you can train. In the middle, you see an 11 by 11 set of pixels, which are the optical reflectivity, essentially, of the Olchi instrument. And so what we do in this, what I will provide you this afternoon is a training data set where we have taken at the center of the altimeter, where there is an echo like this here, all the neighborhood of optical imagery and created a long list of training data sets. So we have these things for several thousand instances of lead and of ice. So it's a balanced training data set that we will use to come up with a trained algorithm to detect leads. So again, remember, a lead is very picky, sea ice is like this. We use those in conjunction with the optical image. So we will use random forest and a novel technique called transformers to test that. So I continue with this lead detection, and in particular in the summer, it's a bit of the biggest puzzle for us and for altimeter experts for 20 years now. In the summer, as you probably know, the ice is melting, the snow is melting, and so you have these ponds of lake, melt ponds, essentially, on the top of the snow and the ice that have very similar properties to a lead. So you have melt ponds and lead. The problem is that the melt ponds are on top of the ice, so they're a bit higher than the lead. And if you remember, the altimetry technique requires you to measure the lead and the ice and take the difference. So if you don't know what's lead and what's melt pond, you are not able to detect the thickness of the ice in summer. And so that was the big limiting factor for 20 years. And we only have winter data for thickness from Chrysler 2. I'll come back to this. But now with this combination of AI and physical understanding, we were able to train several thousands of instances of lead and ice flows in this paper by Dawson last year. With a 1D neural network centered on the lead, we were looking at different indicators of the shape of the echo, how picky it is, before, during, at the lead and after, and trained a 1D neural network to detect this sequence in the track of the altimeter, even in summer. So this was quite successful, as shown in the right. It does false negatives, but it has less than 5% error in attributing leads. So the important thing here is we wanted to be sure that when we measure a lead, it is a lead and not a melt pond. So now we have that algorithm that was published last year, thanks to, in part, some AI techniques. So as I said, leads and melt ponds are very challenging. Melt ponds in particular are challenging and important for the climate system. Melt ponds are dark. There's a lot of research. Some of you are probably interested in that here as well. I think even the organizer was telling me she's interested in that. So melt ponds are very important because they're dark. They cover up to 70% of the surface of the ice in the Arctic in summer, in June, July. And so they can absorb a lot of incoming solar radiation. And it's a positive feedback loop. More dark, more absorption of heat, more melt, and so on. So they've been shown to be very good predictors of the September sea ice extent as well. So there's some nice forecasting models where we use melt pond in June to predict sea ice in September. That is because they incorporate two things: the thermodynamic, the fact that they absorb more heat when they're present, and the topography of the ice. So when there's more melt ponds, it means the ice is smoother, and when it's smoother, it means it's thinner usually. So it's preconditioned to melt. Anyway, melt ponds are beautiful, and they have a specific pond so melt ponds have a special spectral signature at the optical wavelength. So here we took 4 bands in gray of optical signal from MODIS to train an algorithm that I will show you in a second to detect and distinguish between meltponds and ice. So if you take this information for the top, the black line is snow. It's very reflective. The vertical axis is albedo. So you see very reflective snow. You have ponds of different reflectivity, depends if, and ice that is also quite reflective when it's bare. So that's how it looks. Meltponds are beautiful to look at in summer. These blue patches. They're like fractal structures, right? So they're like tens of meters or meters, and they grow and they merge and they form a beautiful pattern. And they're quite hard to detect because they're so tiny. So you need smart tools to do that. They're as small as 1 meter. So what we did is to apply, Sang-Yun Lee published that last year, 2 years ago. He used this neural network again approach with several input layers from this spectral characteristics of the optical signal. And then he used some output layers from meltponds, ice, and ocean, and was able to train a neural network system to detect meltponds, to classify meltponds, ice, and ocean. And so that was quite successful. He then got, in the same paper actually, he used another regression approach, a multinomial logistic regression approach, in order to have a continuous value, not just a classified value. For each pixel, he wanted to know what's the fraction of meltponds. So that's something that you need a regression tool to do, and so he used that technique. And after all this hard work, he was able to produce these maps for 20 years, from nearly 15 years, however long MODIS has been operating, showing the meltponds in different years. And you see that the location of these meltponds, here near Svalbard in July 2013, is quite important. They control a lot of the weather, the climate, the fate of the sea ice. So knowing where they are, when and how is quite important. They're also very important for constraining climate models. So this is a nice example of AI applied to satellite imagery. So the second example, so I'll come back to this, but this is what can happen when you increase the resolution of your satellite imagery. So here we have Sentinel-2, which is a 10-meter resolution as opposed to 500 meter from 300 meter from MODIS. And so this is some work done by a PhD at UCL and Lancaster called Dermot Coe, who's been helping us with this. He's been working for land ice, melt surface on land ice, and he's developed this algorithm that is based on random forest and in combination with Google Cloud. That is a very powerful combination of algorithm and support in the sense that Google Cloud stores all of the Sentinel-2 imagery. So you don't have to go and download this super high amount of volume of data. You can work directly on the cloud, provided, as somebody else said, you're happy to do that. And the proprietary nature of Google Cloud, I'm not completely sure, but I don't do anything that's like a commercial, so I don't mind. But then you can do that very effectively. You can process your data on the cloud and then bring down what you need, which is the classified data at the end. You don't need to have the full processing chain working on your laptops or even on your clusters, because it's really brutal, the amount of data. In Sentinel-2, we're talking about hundreds of terabytes, probably petabytes, to be honest. Am I right? The terabytes goes to petabytes, I'm pretty sure. It's a very big volume of data. So what we did here is we converted that algorithm for a region that I'm very interested in as part of a recent project that just started in Inuit Nunangat. So Inuit Nunangat is this region north of Canada, which is a third of the size of Canada, half of the coastal regions, and it's populated by 60,000 indigenous Inuits. And it's a region that is under rapid climate change. But in this project, we were very lucky to receive some funding with Smart Ice. Smart Ice is a social enterprise, half owned by Inuit and half owned by others, and that has Inuit interest at heart. And in that case, the project was about safe travel on sea ice. So the goal of this project I'm leading with my Inuit counterpart is to provide satellite imagery that will address the two key points that Inuits have identified as problematic for travel, which is roughness of the ice and the snow, how rugged the terrain is, and slush, the wetness of the snow and ice. This is critical because we will work with a location called Pond Inlet. And so in this locality, and like in most of Canada, people drive ski-doos like here. And so these ski-doos have had lots of accidents more and more frequently due to the rapid, among other things, due to the rapid change of climate. So more wet, more fragmented, more rough. And so it's important to understand that the fast ice, where they operate in winter, is really their infrastructure, right? So it's their motorway. So if they don't have this motorway, they cannot go and hunt, they cannot do all of their livelihood habits. So what we aim to do in this project is to provide accurate information of where and when are the slush and the rough ice. So first I will show you how this algorithm is promising to detect slush. In that case, any surface that is melted. So we will actually do that in this afternoon with this software that I find very beautiful, that was developed as part of a ESA Phi Lab, this kind of workshops that they run at ESA, European Space Agency. And I forgot, I think the guy who developed this is called Alistair Francis. But so he's developed this lovely tool that is combines two of my recent interests, AI and painting, because in that case, and you will do it hopefully as well, you open an image like that, which is high resolution on the software. And on top of that, you do your little squiggly drawings by hand on your cursor. And so you classify by hand quickly the regions you're interested in. For example, melt ponds in blue, you zoom in, you draw again. So if you have a good drawing technique, you're probably better at classifying that than if you're crap at drawing, probably not. Well, so you do that and you iterate the training. So you press AI, which is in that case a gradient boosted decision tree algorithm behind the hood, behind the software, and it retrains the whole image. So suddenly you have an image like this. I spent like literally 10 seconds to draw melt ponds, ice, snow, and mountains. And I got this score, which I need to go and understand exactly what it means, but 91% AI score. There's a bit of a black box concept here, but it is very beautiful to be able to rapidly train and create training data sets very efficiently, in my opinion. It combines the visual training with the automatized training. So I think you would enjoy that. It's quite hard to install all the dependencies. So hopefully, if you don't manage, you will see me have fun and draw stuff. But otherwise, we can try and fix it for you as well. So AI for sea ice roughness, as I told you, this is the other key parameter of sea ice that Inuits have identified as problematic for the ski-doos, among other things. But it's also extremely important for all kinds of applications. So the roughness of the ice and the snow is what controls, as I told you earlier, the friction between the air and the surface of the ice. If it's more rugged, there's more friction. So the winds are pushing the ice more, the ocean is pushing the ice more. And it controls turbulent fluxes between the air, the ice, and the ocean. So we really need to understand what are these, how rough is the ice. And to do that, with Thomas Johnson, a PhD in my group, we developed over the last 3 years a very powerful processing chain using MISAR, which is a multi-angular spectroradiometer from NASA that's been flying for 20 years now, that is looking at the surface of the ice and snow and the planet at different viewing angles. It's a passive instrument. So you have 7 viewing angles, a large swath of 700 kilometers, like this one. So the satellite flies and collects information at different viewing angles. We feed that all into a support vector regression scheme. It sounds easy, but it took 2 years to develop. Tom has done an amazing job here, because it's a really big data as well. Each pixel is again 275 meters. So here we're working at 1 kilometer, but it's big data set. And so you feed all this and you train it with airborne data. So we train it with ground truth or airborne truth, which is a topography from an airplane. So we find collocated training data sets, we train the system, and then we expand it to the full arc. And so I think you agree with me that this kind of image is very useful for all kinds of purposes, including operational purposes. So we saw the nice presentation yesterday for shipping. If you are a captain and you're stuck in the Northwest Passage here, near the Barents Sea, and you have this map, you're probably happier than if you don't, because this tells you blue regions are very thin ice, smooth ice, blue, and red is very rough ice, thicker ice. And so you can get that information and travel much more efficiently. So I'm trying to test that with, if you know shipping people in Svalbard that are interested, I'm very keen to discuss and see if we can do trials with anybody who's interested. The other nice thing about this is that it has a very strong repeat. It's in the high Arctic, as long as it's light and you have no clouds, which is sometimes, you can have a good coverage. So you can have, within a week, you can have a pan-Arctic map like this. And that's quite powerful to, because I've been on a Russian icebreaker for Mosaic, and I saw how the Russians work. They get one image every 2 days, and then they try to imagine how the ice will move for the next 2 days. It's not, I hope no Russian is listening, but it's a bit old school. And so, and not only that, but it has only a 2D image, no thickness. This is a kind of, it has an element of 3-dimensional as well, which is very important for the cost, for the risks and so on. So I hope I can work with some of you on this project. So what we did, but in that case, we will develop it also for fast ice with, again, this social enterprise called Smart Ice. You can imagine that ski doing through this ridge terrain is quite hard, right? If you go at 50 miles an hour and you hit one of these ridges, you're probably in trouble. So they want to know where they are and to travel safe and to travel fast. So we just submitted a paper with Thomas Johnson in remote sensing, MDPI, just 2 weeks ago. All right, just to give you a little bit of newsworthy item here. I want to say that physics and AI can come together and give a happy, live together and have maybe not children and live long, forever long, but they can cohabitate, right? So I hope I gave you a flavor that if you use physical retracking of echoes based on a physical understanding of the radar, the snow interaction with the radar and so on, and then use AI for flow classification, as I showed you earlier, you can, and we just proved that, and you can come up to and derive sea ice thickness after a long processing chain with a lot of simulations and physical understanding. We can come up with something that is very, very exciting. What it is the complementary to that. So until now, really, it's just hot off the press, before the press, I'll tell you in a second, we had 6 months of data of sea ice thickness. So this is from January to April, then nothing. And then from November to December, we have sea ice thickness. Only when it's dark, when it's cold, when it's winter. Or the winter in a kind of loose term, half of it. These quantities are extremely important. Thickness is critical to predict sea ice evolution. It really tells you how much ice there is in total. It tells you where it melts, where it grows, how thick it is. It's critical for shipping. It's for forecasting. It's critical for weather forecasting and so on. It's critical for model initialization, for model validation, etc. So since next week, we have a high impact journal paper that will show these results. So I can't tell you too much about it, but we have now, thanks to the work by Jack Landy and a project I was co-leading with him, we are and other projects, we have been able to fill the gap. So we have 6 months of sea ice thickness. Now we have, thanks to AI, together with physical understanding of the cryosphere and radar altimetry, we're able to fill the full seasonal 12 months. And so now we are from May all the way to October. So we're somewhere here now. Svalbard, I can't remember what year it is, but now, from now on, you will have maps like this. They will come up next week, 15th of December. You should have some. It's a Norway paper as well, because he's based in Tromsø. So there will be quite a lot of discussion on that in the news, of how you can now use sea ice thickness in the summer to predict what's going on, to plan your activities, for shipping, for ecology, for all kinds of things. It's also, I forgot to say, but the studying biology and so on is very critically linked to sea ice thickness as well. The light availability through the ice is critical for phytoplankton, life under the ice, and so, for fishing, for all kinds of applications. So I hope you're convinced that combining physics and AI is a good thing. So So the paper is by Landy in 2022, and it's going to be in Nature, on Wednesday, on the 15th. I hope they won't retract just because this. Anyway, so optimize interpolation, third pass. I'll go a bit quicker on this one. Gaussian processes and other little goodies of AI that I used and with my team and colleagues. So normally when you do a regression, linear regression, you try to predict Y, knowing some observation X, some input X, output is Y. It can be a forecast, or it can be an optimal interpolation, or it can be any kind of regression. And then you try to predict this weights or regression parameters beta. And so the Bayesian linear regression approach is when you make Y not just one value, but a probability. So you're trying to predict an entire probability distribution. And so these ideas that I will talk about, but I won't do the math, is largely based on you're trying to find the probability of all these parameters beta, knowing the observations and the input, and optimize this fit. So interpolation is typically what you see here. What's the best line you can get through data? And sometimes interpolation is better than just the data themselves, binning or something. So because you invent data, but if you do it in a smart way, you're actually gaining in understanding. So I'll give you some example of that, starting with a paper we published last year with William Gregory, a very smart PhD student of mine, who's now in Princeton. We did some amazing work with statistics and AI and unsupervised and supervised techniques. One of them, a lot of that was on Gaussian processes. So here we have, we live in the golden era of radar of altimetry. We have CRISAT-2, we have Altica, we have Sentinel-3 A and B, we have ISAT-2 now, the $1 billion American NASA satellite, very beautiful tool. So we have all these altimeters, and we need really to combine them. So if you have one at a time, you get tracks like this on a single day. If you merge them all, you see that the coverage gets much better. Nevertheless, on a given point, on a given day, you have nothing. So you want to take all the information in a surrounding 300-kilometer radius, that's what we did, to invent the data here. Not only in the neighborhood for a given day, but also 1, 2, 3, 4 days after, 1, 2, 3, 4 days before, and optimally interpolate all this information into a consolidated daily product. That was what we did in this paper. And we came up with these maps that we're still trying to understand how robust they are, how good they are, but they showed us some promising new insight into physics. Because if you have daily resolution now, you can probe new processes in the climate system that you couldn't at monthly timescale. Typically, the maps are produced at monthly average timescale. So we have the maps and we have the uncertainty on the maps. So this is the other advantage of Gaussian process techniques, is it provides you an uncertainty directly, it's built into the methodology. This was a technique when we worked at grid level. You can do the same kind of optimal interpolation along the track of the altimeter. So the old technique is quite small, is shown here. In blue, you have the ice elevation along the satellite track. The satellite track goes from Greenland to Russia. You have red points, which are the lead position along the track. And so you want to detect the leads. In some places near Greenland here, you have only a few leads. So you do a massive interpolation, connect the dots, essentially. That's the old way of doing it. The more innovative way of doing it is to account for tracks, not just along the track, but look at tracks that are neighboring tracks in time and in space, including from other satellites, perhaps, and interpolate the elevation of the ocean in a much more robust way in this black line, and capture all the lead position. And you see that sometimes the measurement of the lead from the altimeter is wrong. You have errors in the measurement, so you discard actually some data. And that allows you to improve the accuracy of the elevation of the ocean and also the sea ice thickness and freeboard and so on. So one application, of course, of that is dynamic ocean topography. This is oceanography now. So if you connect all these dots of the leads, you do this magic thing, which is to measure the topography of the ocean through the ice. So when you look at the maps of satellite imagery, you think there's no way I'm going to measure the ocean elevation. Actually, you can, because you have these cracks everywhere. And if you connect all these dots and make a a full map of the ocean motion up and down in time. You see this so-called dynamic ocean topography, which is what controls the main current, the large-scale geostrophic currents, and also is important to understand Ekman transparent zone. So in that case, I show it here for the Arctic. It's some work we did, and this is some work done by colleagues in France at CLS, in Antarctica as well. And if you improve and optimally interpolate the processing, you start to see features that are finer and finer. And actually here in the open ocean, you see eddies, big eddies, but you see these eddying structures. So this is something I'm interested to improve the resolution thanks to optimal interpolation, can improve the physics you're able to probe in time and in space. I think I'm running out of time. No, I've got 10 minutes, a bit less. Yeah. So this is some, it's called ocean, polar remote sensing of the ocean. I'm going to quickly go on this one because I find it's a very promising technique. Again, I'm in earth sciences, so I talk to geophysicists, and they've done stuff that we haven't done yet 20 years ago for seismology and stuff like that. So they use these kind of techniques, which are, say you have this map on the left here. I don't know, it could be anything. It could be a dynamic ocean topography. So you have the reality is the color map, and then you have observations, and the observations can be sparse. And you're trying to deduce the full truth from sparse observations. So how you do that? You could do optimal interpolation like I showed you with Gaussian process. But actually there's techniques called reversible jump Markov chain Monte Carlo that has been applied for geophysics and also in ocean physics actually recently to create a tessellation of the space that you're sampling like this. Every point that you measure, you create a Voronoi or a Delaunay tessellation around it. But what's special in this kind of statistical approach to infer the data, to invert essentially the data, is that the sampling is also a random process. So you can the places where you want to estimate values. So sorry, these are not the measurement places; they are the parameter space. You can create cells, and if you gain information by creating more and more value in these places, you get finer and finer resolution. Say in this place I have lots of measurements, then for sure I want to have finer resolution. If in another place I have very little observation, then the cell will be bigger. So this is a kind of very smart concept to allow you to invert for something. On the right is the invented data. It's not the best example, but it does work. This is very good to also, on the contrary, inform you where you want to do the campaign, the field work. If you're missing information somewhere, probably you want to go and deploy a field campaign or airborne campaign. So this is complementary to this planning ideas. So I continue with some Gaussian process ideas. Again, William Gregory did some amazing forecasting work at the time, and I think we're not anymore, but at the time we were the leading statistical forecasting system in predicting sea ice extent, global sea ice extent, sea ice concentration. So this is the typical decline. For those who don't know, we lost half of the sea ice in the last over my lifetime. And here you see it very dramatically, I believe. Those who've been here for a while, I've definitely seen it. And so we want to predict that. So for a long time, there's been a sea ice prediction network exercise led by Julian Strover. And here we wanted to do a prediction based on Gaussian processes. So we did it, and we did some forecast from June, July, and August of September in red, blue, and darker blue. And black is the reality. And we're able to capture very well the total extent, but not only that. With 1 month lead time, 2 months lead time, and 3 months lead time, we have skill of more than 0.5, which is quite amazing, really. And we're able to say 1 month, 2 months, 3 months ahead, how much sea ice there will be in this region. This is very good for planning. Again, if you're a Russian and you want to plan your season of shipping around the Russian coast here, if you have the information 3 months ahead, it's very important. This is competitive with climate model forecasts because climate models have got their own issues. So it turns out that purely statistical forecast methods are still competitive with fully coupled initialized climate models. You would think that eventually the climate models will win, but for now, these techniques work well. I'm almost done. I want to show you a few things on unsupervised clustering as well. So some of you might be familiar with principal component analysis, PCA. You have spatial temporal variables, and you classify them in simple modes of variability. There's another way to do that. We do, again, with William Gregory and Julian Struggle, we developed this technique, and Peter Solich, is to classify. I'll give you a general example here of the climate, the sea surface temperature. You find the regions that have similar behavior of variability. So in that case, you have ENSO, the large eastern equator, Pacific equator signal. So these regions vary in a kind of common way. So it's a simplification of your system. You don't need to have every single pixel. You simplify your problem into this kind of regions, thanks to this complex climate network. I'm not going to the detail. That was published also 2 years ago, and again we tested that on climate models. And you get a network, and then you can see linkages between the networks. So we've done that for the Arctic as well, Arctic sea ice concentration, and that's very informative. You see different regions, how they are correlated, how strongly correlated they are, and so on. And this can be used for forecast as well. So in that case, you see that ENSO, this region is obviously very strongly correlated with a lot of regions, and it's representative of the El Niño Southern Oscillation. So as I said, we did it also in the Arctic with different variables, and this is some work that will perhaps will continue on multi-layers network, where you bring sea surface temperature, in that case, temperature of the surface and sea ice concentration, and try to see all the linkages at given time and with a lag time, and so it gets messy. You get these big complex networks, a bit like Facebook, let's say, but for the climate. And so you have June, July, August forecast, where you can try and do forecast maps. I want to give a little credit to a colleague of mine in Bath called Anderson. I think I'm second choice. I think he was invited first, and he was very kindly turned it down. No, he couldn't make it, and he was very kind to suggest my name. So he's a very young, upcoming, smart AI scientist, I would say, who's done some nice work with this IceNet. He got some good branding as well. I'm slightly jealous. We're not competing, but we did another focus that's, I think, competitive, but it's much less. No, I mean, that is very exciting work, but in terms of skill, I think we're still doing competitively well. But that is very interesting because it uses ideas of deep learning. So what the concept in a nutshell is, we use deep learning on a climate model to pre-train your understanding. So the deep learning is a machine. You train it on climate models, understanding all the teleconnections, sea ice, pressure, air, temperature, all kinds of teleconnections that allow you to better understand the maps of sea ice 1 month, 2 months ahead. In that case, I think they publish 1 month only ahead, and they do get a very good score. But the general methodology of training on a model to then train on the real world and have a system that's ready to be learning in the most smart way, I think it's quite a smart idea. And it's something that's happened in all fields of science, and I hope to do more of that in the coming years. The last one is credit to our team, because science could not happen without validation field work. And that was deployed on Mosaic, and since then, several times. It's an amazing QK radar built and developed by Julian Struggle, here analyzed by Rosie Willett and several other people, Vishnu Nandan, Robbie Mallet, and others are working on this, Thomas Newman. A lot of people in our group are working with this radar. And what it does, it is kind of simulating the future mission Crystal in a way, from the ground. So Crystal is the QK satellite mission, follow on from Cryosat in a way, and that's going to be launched now. And we want to understand how the KU and KA radar penetrate or not into the snow. So here what you see is a plot by Rosie. You see that you can have a very good comparison between a Magna probe, so this is an actual measurement of the snow, and this KU and KA signals. And so what we did is, instead of trying to do basic linear regression, we tried with several master students actually, and we squeezed all their AI intelligence, and we understood just about what they were doing. And at the end of this exploitative process, we now have a nice deep learning approach using Kera's API, which some of you might explain to me what it is exactly, but we use a technique, we use also CNN, and we have this kind of nice strong regression, 0.7 regression between the observation and the combination of radar signals. And so we're able to measure snow thickness essentially, which is quite exciting. All right, so I'm going to stop here, give you 5 minutes at least for questions. Oh, it's not even, so I'm sorry about that. I just finished on time. This is teamwork. This is UCL. I hope to see you all, your smart AI people soon, or physicists, or mathematicians, or artists, or whatever, to join us at UCL. Pay us a visit. UCL is a nice place. And all these people have helped along the way develop all the results I've shown here. So thanks so much.